In Volume 1 of What is Tccs, we talked only about EFI. Now, in Volume 2, we will discuss the other remaining TCCS functions. That is, Electronic Spark Advance, or ESA. Idle Speed Control System, or ISC. A special air intake control device called Toyota Variable Induction System, or TVIS. The diagnostic function. The fail-safe function. And the backup function. The TCCS is used with various engine models, and although the TCCS construction and operation for a particular engine may differ from those for other engines, we would like you to remember that all TCCSs operate in basically the same way. In this video presentation, we will focus on the TCCS that is used with the 4AGE engine. Now, let's take a look at the Electronic Spark Advance, or ESA. First, let's talk about the sensors. A pair of sensors is built into the distributor. One is the NE pickup sensor, which detects the crankshaft angle and the engine speed. The other is the G pickup sensor, which detects the standard crankshaft angle. The vacuum sensor detects the intake manifold pressure. The throttle position sensor has two functions. It detects whether or not the throttle is fully closed, and it detects the throttle opening angle. When the engine is cranking, the ST terminal of the ignition switch informs the ECU of this. The water temperature sensor detects the temperature of the engine coolant. Each sensor sends a signal to the ECU in the form of either a voltage or a pulse signal. Furthermore, as long as the air conditioner is operating, the air conditioner amplifier outputs a voltage signal that keeps the ECU informed of this. The ECU calculates the ignition timing that best fits the running conditions of the engine based on signals from the various sensors and data stored in its memory. It then sends an appropriate ignition signal to the igniter. Therefore, the distributor on an ESA-equipped engine is constructed somewhat differently from that used with a non-ESA engine. Let's see what a distributor used on an ESA-equipped engine looks like. As you can see here, it does not have a mechanical governor advancer or vacuum advancer. Instead, it has two pickup sensors. As we explained before, one is the NE pickup sensor, which detects the crankshaft angle and engine RPM. The other is the G pickup sensor, which detects the standard crankshaft angle, which is used by the ECU in determining the output timing of the ignition signals. Let's see just how the ESA system controls the ignition timing. We are now looking at the basic circuit diagram of the ESA. As you can see, the ESA system consists of the distributor, various other sensors, the ECU, the igniter, the ignition coil, and the spark plugs. The ECU receives signals from the sensors that detect the running conditions of the engine. It also contains optimum data regarding ignition timing. The ECU selects an optimum ignition timing from this stored data based on the signals it receives from the sensors. Just before the crankshaft reaches the angle at which ignition is to take place, the ECU sends an ignition, or IGT signal, to the igniter. Based on this signal, the igniter actuates its power transistor, causing current to flow to the primary coil. When the crankshaft rotates to the ignition angle, the ECU stops sending the ignition signal to the igniter. This causes the igniter's power transistor to be turned off, halting the flow of current to the primary coil. This, in turn, causes a high voltage to be generated in the secondary coil, causing the spark plug to fire. At the same time, counter-electromotive force is generated in the primary coil, so the igniter accordingly sends an ignition confirmation, or IGF signal, to the ECU. Now, we will see briefly how ignition timing is controlled. In the ESA, ignition advance is determined by three factors: the initial ignition timing, which is determined by the angle at which the distributor is physically fitted to the engine block, the basic ignition advance angle, and other supplementary ignition advance angles. The latter two, that is, the basic ignition advance angle and the other supplementary advance angles, are controlled by the ECU. Now, let's see how the ignition timing is controlled in accordance with the driving conditions, beginning from the moment the engine is cranked. During cranking, and immediately after the engine has started, the ECU cannot calculate ignition timing accurately because the engine's speed is not yet stable. For this reason, the ECU does not calculate the amount of advance when the starter motor is operating or when the engine's speed is low. Instead, the ignition timing at these times is fixed at 10 degrees before top dead center, as determined by the angle to which the distributor is physically set when mounted. This is referred to as initial ignition timing. The ignition timing at this moment may be shown graphically like this. What happens to the ignition timing during idling? When the engine's speed reaches a predetermined RPM, the ECU determines that the engine has started and begins controlling ignition timing. If the throttle valve is fully closed at this time, the ECU advances the ignition timing beyond the initial ignition timing by an amount determined by the engine RPM. This is referred to as the basic ignition advance angle, shown in yellow on the graph. Now, what will happen when the accelerator pedal is depressed? The ECU judges from the signals sent by the throttle position sensor that the accelerator pedal has been depressed. It then determines a basic advance angle based not only on the engine RPM, but also on the manifold pressure. Furthermore, the ECU adds other corrective advance angles in accordance with engine conditions. such as when the air conditioner is operating while the engine is idling. Or when the coolant temperature is low. These are referred to as supplementary ignition advance angles and are shown in blue on the graph. Next, we'll talk about the idle speed control, or ISC. The V-type ISC is used with the 4A GE engine. We will now illustrate how the V-type idle speed control works. As you can see here, a bypass is provided between the throttle body and the intake air chamber. In this illustration, the bypass passage is closed off by the vacuum switching valve, or VSV. While the engine is cranking, the ECU is informed of this by the signals from the ST terminal of the ignition switch. Based on these signals, the ECU sends current to the VSV. As you can see here, the bypass passage opens up so that more air can flow into the intake air chamber. This is to make engine starting easier. Immediately after the engine has started, the ECU continues to send current to the VSV for 10 seconds in order to stabilize the engine idling speed. After 10 seconds have passed, the ECU stops sending current to the VSV. Now, we'll discuss the Toyota Variable Induction System, or TVIS. TVIS is designed to improve the efficiency of air induction into each cylinder throughout all engine speed ranges. This is also controlled by the ECU based on the engine RPM signals. Let's look at another illustration that shows TVIS functions. As you can see here, each intake manifold is divided into 2 passages, and an air control valve is fitted in one of these passages. When the engine is running at low to medium speeds, the ECU causes current to flow to the vacuum switching valve, or VSV, to close the air control valve. Therefore, air passes through the manifold at a high speed. The air intake efficiency is improved in these speed ranges due to the inertia of the moving air. Closing the air control valve also creates a strong swirl, which improves combustion stability. However, induction resistance increases as the engine speed rises. When the engine RPM increases beyond the medium speed range, the ECU stops current flow to the VSV. This causes the air control valve to open so that a sufficient amount of air can be easily drawn into the cylinders. As we have just seen, the TVIS is controlled by the ECU in accordance with engine RPM to improve air induction efficiency. Now we'll discuss the diagnostic function of the Tccs. If an open or short develops in any sensor or its related circuitry, data on this malfunction is stored in the memory of the ECU in the form of a trouble code. In most cases, the check engine lamp also comes on to warn the driver of the malfunction. The technician can determine the nature of the trouble by causing the code to be output from the ECU. To do this, he shorts terminals T and E of the service connector with the throttle valve fully closed and counts how many times the check engine lamp blinks. Two types of service connectors are used with the 4AGE engine, depending on the vehicle model. A 2-pin type, as was shown before, and a multi-pin type, as shown here. In the case of an AE86 Corolla, for instance, this is a code indicating a normal condition. And this is a code indicating a malfunction. This particular code indicates an open or short in the water temperature sensor or its related circuitry. The types of trouble codes used and the way in which the codes are indicated vary depending upon the vehicle model and/or engine type. These are explained in detail in relevant repair or diagnosis manuals. Next, let's talk about the fail-safe function. If a sensor or its related circuitry should malfunction, the ECU would continue to control the Tccs based on the signals from the faulty sensor. This could lead to rough idling, poor acceleration, etc. The fail-safe function is provided to prevent this type of trouble. When the ECU receives a signal indicating a malfunction, the ECU begins to control the Tccs based on the data that is stored in its memory rather than by the signals sent to it by the faulty sensor. Depending on the nature of the trouble, it may even stop the engine. This function is called the fail-safe function. In the case of the 4AGE engine, the fail-safe function begins operating under one of the following conditions. First, it operates if an open or short develops in the water temperature sensor, the intake air temperature sensor, or their related circuitry. If this occurs, the ECU continues to control all systems as if the coolant temperature were 75 degrees centigrade and the intake air temperature were 20 degrees. Normally, the fuel injection duration is corrected by these two signals. Therefore, if there is an open or short in one of these sensors or their related circuitry, the amount of fuel that is injected is not corrected based upon the coolant temperature or intake air temperature. Furthermore, if there is an open or short in the water temperature sensor or its related circuitry, correction of the ignition timing is not carried out based upon the coolant temperature. Second, the fail-safe function operates if, due to an open or short in the throttle position sensor or its related circuitry, the ECU becomes unable to detect the angle to which the throttle is open. If this occurs, the ECU controls the system as if the throttle opening angle were 25 degrees. Finally, the fail-safe function of the TCCS is actuated if the ECU fails to receive an ignition confirmation, or IGF signal, from the igniter. When this occurs, the ECU judges that a problem has developed in the ignition system and stops sending injection signals to the injectors. Finally, we will discuss the backup function. If the central processing unit, or CPU, of the ECU itself becomes defective, the ECU will become unable to output ignition, or IGT, signals to the igniter. The backup function is provided to prevent these problems. How does the backup function of the TCCS ensure continued engine operation? First, when the backup function is operating, the ECU selects a predetermined injection duration from the backup data in its memory based upon signals from the ST terminal of the ignition switch and the throttle position sensor. The ECU also controls the injection timing based upon signals from the distributor. The backup function also controls the ignition timing based on signals from the distributor, the ECU fixing it at 10 degrees before top dead center, that is, the initial ignition timing. The backup function of the TCCS is also actuated if an open or short develops in the vacuum sensor or its circuitry. The fuel injection duration and ignition timing are controlled in the same way as they are controlled by the backup function when the CPU becomes defective. The 4AGE engine was used as an example for the purpose of this technical video. In the case of other engines, functions and methods of control may vary depending upon the type of engine. However, the TCCS operates in basically the same way in other engines as in the 4AGE engine. We recommend that you refer to relevant STIs and other manuals for more details. This brings us to the end of Part 1, Volume 2 of our video presentation on the Toyota computer-controlled system. It is important that you fully understand the contents of this technical video program. Only when you do can you say that you have truly understood the basic functions of the TCCS.